So we are going to talk about the binomial distribution today. A binomial distribution is kind of a special case of everything that we have been doing. So there are a few requirements that we need to look at. If you have your formula sheet handy, so we're in chapter 6, so we're going to be talking about a few things on the binomial distribution. You'll see the third bullet under chapter 6 has the actual distribution, P of x for probability, but you'll notice it has a lot of different variables in here, an n, c, x, p, so we have to kind of figure out what all of those things mean. The key things, if we are going to have a binomial distribution, it has to meet a certain set of requirements. The first, you have to have a fixed number of trials. I can't be doing this until I get a certain result. I have to decide ahead of time. I'm going to do this 5 times and see what happens. The trials are independent, so it's not like drawing a card out of a deck and trying to find the probability of getting 5 clubs, because once I take that first card out, it changes the probability for the next one, right? We did a lot of those on our quiz where every time you took one out, the total number dropped by 1. So if it's independent, I would have to take my card out, look at it, and put it back in the deck. So the probability is the same every single time. For each trial, we can only have 2 possible outcomes, success or failure. So if I'm looking at my deck of cards, and then it could be a club or not a club. Okay, I'm not trying to find the probability of getting each suit. I have 2 outcomes, success or failure. And the probability of success is fixed. Every time I have the same probability of success. So I would jot these things down, because when we start looking at different distributions, the first thing we're going to try to decide is it a binomial? Because if it is, our probabilities become a lot easier to calculate. So you need to know what the requirements are to be binomial. So binomial, bi means 2, we have 2 outcomes. And we're going to run it a set number of times. Each time is independent of the others, so we don't have to look at what happened the first time to know what's going to happen the second. The probability of success is the same every time. So I just want to look at a few scenarios and decide if these would be binomial or not. So a player rolls a pair of fair die 10 times. The number x of 7s rolled is recorded. So if it's binomial, we have to have n, a set number of trials. Are we running this a set number of times? 10 times. So we met that requirement. The trials are independent. When you roll a dice, does that change what you roll the next time? No. So they are independent. So that's good. Each time there have to be 2 outcomes, success or failure. What are my 2 outcomes here? Yeah, 7 or not a 7. So we have 2 different outcomes. Is the probability of success the same every time? So every time I roll, do I have the same chance of rolling a 7? Yes. So this would be binomial. So we have 10 trials. My outcomes are 7 or not a 7. They are independent. The same probability every time. So this is binomial. It meets the 4 requirements. You don't necessarily have to write down all that information I did. I'm just kind of jotting that down to show you the things that I'm thinking about when I decide if it's binomial or not. All right, the next one. An official with the FAA randomly selects airline flights until she finds 10 that were not on time. The number of flights X that needs to be selected is recorded. What do you think? Is this going to be or not?
Because there's a certain number of times until you get to 10. So that could be 250 until you get 10.
Exactly. To be a binomial, I have to know before I ever start how many flights am I going to look at. But she doesn't know. She just knows she's going to keep getting flights until she finds 10 that were not on time. So it could be the first 10 flights she looks at, or she may have to look at 20 flights, or 30, or 40, or 200 flights. So this is not binomial because there's not a fixed number of trials. See. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. Are there a fixed number of trials here? Yeah, we are going to pick 4 students, so there's 4 trials. Are there 2 outcomes?
Yes.
Yeah. Female or not. So that's good. Are they independent?
Yes.
So let's think about our class. Right now, we wanted the probability of being female. Okay, so how many people do we have in class today? 12. How many of you are female? 8. So the probability of the female right now is 8 out of 12. Okay? So if I select somebody, so let's say I select Maddie. She comes up to the front of the room. Now I need to select another person. What's the probability of that person being female? 7 out of 11, right? Because I've already took one person out. So are they independent? No, because once I take that first person out, it changes the probability for the second one. To be binomial, everybody has to be the same probability. So, in this case, these are not independent. So that means it is not binomial. What could I change about that to make it binomial?
One person is selected and then put back.
Yeah. I select Maddie, but then she sits back down and she could be selected again. If I did it that way, would it be binomial? Yes, because the probability is the same all 4 times. Is this one okay? So the way it turns out is when you're finding probabilities for a binomial, there is a shortcut to it. So if I were, let's do something simple. Let's say I'm going to roll dice, okay? So I'm going to roll it 3 times. And I want to record the number of 6s I get. Would this be binomial? Do I have a set number of trials?
Yes.
Are they all independent? Yes. Do I have 2 outcomes? 6 or not a 6? Because I'm not recording everything I roll, just 6 or not. And is the probability of rolling a 6 the same every time? Okay. So if you think about this, the first time you roll, you could either get a 6 or not a 6. So when we're finding these probabilities, in general, they use P is the probability of a success, which in this case would be a 6. What's the probability of rolling a 6? 1 out of 6. Q is the probability of a failure. So in this case, that would be not a 6. What's that probability? 5/6. Notice, what do those 2 add up to? 1, because they're the only two outcomes, so they're complements of each other. All right. So if I asked you to find the probability distribution for this, we could actually count up how I rolled and how many 6s I got and the probability of each. What would be the possible outcomes for the number of 6s I rolled? 0, 0, 1, 2, or 3, right? I'm only rolling 3 times. Okay. So let's see if we can figure out what these probabilities would be. So to get 0 6s, what did I roll every single time?
No.
Not a 6. So what's the probability of not a 6? Okay, so it'd be the first time I didn't roll a 6, the second time I didn't roll it, the third time I didn't roll it. So you could actually find this probability. If I wanted to get 1 6,
1 6 times 5 6
means the first time could be a 6 and the next 2 weren't. Or, we kind of had some like this on our study guide, didn't we? Could it be that the first and the third one weren't, but the middle one was? So if the first one isn't, but the next one is, but then the last one isn't. Or it could be that which one was a 6? Yeah, I'm going to show you a shortcut for how we're going to do this, but I'm trying to explain what the binomial is doing first. So there's really, to roll 1 6, there's 3 different ways that could have happened. It could have been the first one I rolled, or my 6 could have been the second one I rolled, or my 6 could have been the third one I rolled, right? So could we add all these up? Yeah, it's just a matter of pushing some buttons. So if I did this, we have 0.3472 approximately. No rounding error here. Okay. To get 2 6s, how could that happen?
It could be 1 6 times 1 6 times 5 6,
Okay,
or
so-
it could be 5 6 times 1 5 6 squared.
Okay, so it could be that I got a 6 on the first and second, but not the third, or I could have not got it the first time, but got it on the second and third, or I could have got it on my first and my third, but not my middle one, right? Okay, so I could find this probability. And the final outcome, 3 6s, there's only one way that happens, if all 3 of these are 6. So what's the downside of this? I could do it that way. It's time consuming. I only had 3 outcomes here. What if I said, okay, I'm going to roll the dice 10 times? Then I have to think about every combination to get 6s out of the 10 times I rolled it. So this is very, very time consuming. But if you notice, we're really multiplying the same things every time. You know, the first one, I had 5 6 3 times, and I didn't have any of the 1 6. These, we had 1 6 once, and we had 2 5 6. Okay, so we're adding up the same probabilities every time. There is a shortcut for this. This is on your formula sheet. This is how the binomial distribution is calculated. So in this, N is the number of trials. I already wrote out on the last one, P is the probability of its success, and Q is the probability of failure, or you might see it as 1 minus P. All right, so in this formula, the NCX, this is actually a probability calculation. It's called a choose X. There's a formula for that, but we're really just going to use our calculator to find it. Well, I'll leave it right for a second. So you don't have to memorize how to do all those things. P is the probability of getting what we want. Then Q, or 1 minus P, is the probability of that not happening. If you press the math button and you go over to PDR at the top, that's probability, and the third thing down says NCR. So we will use that function when we're trying to put these in. So you'll go to math, over to probability, and the third one, NCR. So we're going to do an example in a minute, and I'll show you how to actually use that, but I wanted to make sure you knew how to find the function in your calculator. Okay, so we're just going to calculate some probabilities. According to the Experian Automotive, 35% of all car-owning households have 3 or more cars. We have a random sample of 20 car-owning households. So N is 20. That's the number of trials I'm looking at. We are finding the probability that they have 3 or more cars. So that is 0.35 for my P. So part A, I want the probability that exactly 5. So X is 5 in this scenario. We want 5 of them to have 3 cars. So look at our formula. It tells you want NCX. So my N is 20. C, my X, how many am I choosing? That's my 5. Okay, then it has P. So the probability of having those is 0.35 to the X power. So that's 5. 1 minus P, so 1 minus 0.35, 0.65, to the N minus X power, so 20 minus 5 is 15. Basically, if we have 20 trials, 5 of them have it, 15 don't. So then to do this on your calculator, I'm going to start with the parenthesis. And I need to type in my 20, and then you go into math, probability, number 3. So it'll say 20 NCR, and then I type my 5. And I'm going to close that parenthesis. Did everybody get the 20 NCR 5 entry? And I'm just going to put this all in at once. So then my next parenthesis is 0.35 to the 5th, and 0.65 to the 15th. 5 of them have it, 15 don't. So we get a 0.1272 or 12.72% chance. We have these p-values. Those are some of the common probabilities. It's not going to have everyone, so we have to be able to use the formula. This was 0.35, so we see we do have a 0.35 column. My n was 20, so the n's are out to the side here. So my first page has 2 through 7. The very last thing, the back page, has the 20s. Okay, so does everybody find that very last page of our chart? So when my n is 20, then my x, if you go over to x, we were looking at 5, and go over to your 0.35, it has 0.1272. So it has some of the common ones calculated for us. All right, so let's try using this table to find some. The second one, I want the probability that less than 4 have 3 or more cars. So less than 4. That means it could be 0 people, or 1, or 2, or 3, right? So we're still looking at, my n is still 20, and my probability is still 0.35. So I'm looking at this. And less than 4, so it could be 0, or 1, or 2, or 3. So what you have to do is add up those 4 numbers. And what do we get? 0.0444. Oh, yeah, 5, sorry. I will say there is a slight rounding difference, so we could have calculated this on our calculator. And if we had put them all in our calculator, it came out to 444, so there is rounding error. So please, if you're just adding numbers from the table, write down the 4 numbers you're adding so I know how you got your answer. All right, C. I want the probability that at least 4. So at least 4 means what? 4 or more. So we have the table in front of us. It's not that big of a deal, but we would have to add up 4 through 20. You notice when you get to the bottom, it says 0.0000 with a plus sign. That means the first 4 digits are all zeros. It's still a positive number, but it's a very, very small chance. So we could add up all those, or we could realize we just found the probability that it was less than 4. So we could just do 1 minus. So you should get 0.9555. The last one, I want the probability between 3 and 5. So between 3 and 5. So that means x could equal 3, 4, or 5. So what should I do with my probabilities? Just adding up those from the table. So the probability of 3 plus the probability of 4 plus the probability of 5. And you guys add that. Tell me what you get. What is it?
3.
2, 3, 1, 3. Is that what you guys got? So you have choices now. You can either use the formula or use the table. Just please make sure I know how you're getting it. So if you're using the formula, write it out like I did on part A, where I wrote out the formula. If you are doing it from the table, then show the work like I did on my sticky note where I put the numbers I was adding together, just so I know how you're getting your answer, because the numbers in the table are all rounded to 4 decimal places. There is a slight difference sometimes due to rounding error, so as long as I know how you got there, that part is fine. Is that okay? We can find the mean and standard deviation of the binomial distribution as well. So we had formulas for a regular probability distribution. Here is specific to the binomial, and again, this is all on your formula sheet. So the mean is just n times p, so the number of trials times the probability of success. Your standard deviation is the square root of n times p times 1 minus p. So a much easier standard deviation formula than we're used to. We don't have to make any big table and square a bunch of things or anything. We're just plugging in our n, p, and 1 minus p. I would like to do an example with this, and then we'll probably stop there for today. So our same scenario, 35% of all households have 3 or more cars. So that's my P. But this time I'm not just going to look at 20 of them. I have a random sample of 400. So what does that 400 represent? N. And I want the mean and standard deviation. So formula for mean is just n times p. So just 400 times the 0.35. So we get 140. Standard deviation is the square root of n times p times 1 minus p. So that's 400 and 0.35 and 1 minus 0.35, or 0.65. We get 9.539. Alright. I'm stopping here. I'm not done with the section yet, so we will work on finishing this tomorrow. But let's go ahead, we can try some. Take 14 even. All of those are just telling me if it's binomial or not a binomial.
The A, C.
Yes, part A and C. I think I'm just going to go ahead and give you the whole assignment rather than breaking it up for today and tomorrow. Technically, you do know how to do all of it, but tomorrow we're practicing some more, and then we should have some time to work on this as well. I'm sticking with what I've been doing on the other, so unless the only thing the question asks for is to interpret, you don't have to. On a lot of them it says find and interpret, you don't have to, but if it says part B, interpret this, then you have to do